Welcome today to the topic of charge. What is charge? What are conductors? What are insulators? Today what we're going to be talking about is the property of charge. In particular, what I will introduce is the charge model. I will talk about charge diagrams, talk about the principle of charge conservation, charge quantization, and then look at some simulations for how charge actually behaves. So when you think of electricity, when you think of charge, probably a number of questions come to your mind immediately. Some of those questions likely are, well, first of all, why does static electricity crackle? Here's some questions that I wrote down. Why does the entire universe appear to be charge neutral? Why are there only two types of charge? Why do the two types of charge appear to be exactly the same size but opposite effect? In fact, it appears to be so down to less than 1 part in 10 to the 21. Why is charge conserved? Why can't we create charge? What is the essence or the very nature of charge? Where is charge located within particles? Why do protons and electrons even carry this property of charge to begin with? So charge is the whole basis for this course. So let's talk a little bit about charge diagrams. Now, in any ordinary chunk of material, there is going to be essentially Avogadro's number of charges. So in a chunk of material, is going to have somewhere on the order of 10 to the 23 electrons. Now, electrons carry a negative charge, and protons carry a positive charge. So 10 to the 23, that's a very large number of charges. Why don't we really experience the effects of that? Well, the reality is you do. That's what keeps you from falling through your seat, or your feet from falling through the floor, or my hands from falling through, being able to push through the countertop. There's an electrostatic repulsion that's taking place. But why is it when I take two chunks of material and bring them together, I typically don't experience a force? And that's because most materials are, or large chunks of materials are charge neutral. So a big chunk of material is charge neutral. And what this means is that there's equal numbers of positive and negative charges, so we don't really see the effects of charging. So in order to actually see the effects of charge, what you have to actually do is you have to add charge or take charge away. Now, a charge diagram represents the excess. I should say excess or deficiency of charge. We don't want to, when we draw a charge diagram, we're not going to try to sketch all the individual microscopic charges that are there, but it's just a representation of any extra charge that has been added or any extra charge that has been taken away. So for our purposes, we're going to talk about two different basic kinds of material. First of all, we have the conductor. So two types of materials. Now, in reality, the spectrum is a little bit more broad than this. In fact, there are materials such as semiconductors, which kind of would be somewhere in between an ideal conductor and an ideal insulator. But first of all, I want to talk about a conductor. So a conductor is simply a material where electrons are free to move. So the electron moves freely. Oftentimes we talk about a sea of electrons in a conductor. We might talk about a sea of electrons that kind of dance around together, and they're not particularly bound to any particular atomic nuclear core, but they can more or less move freely about. Basic properties of a conductor. Now, what gives rise to this is that, for any real atom, there's going to be multiple electrons. Now, all of the electrons don't move freely, but in particular, typically it's the valence electron that's weakly bound, and that's the one that is not tightly held to that particular atom and is free to move. So it can sort of dance about freely throughout the material. And then we have what is called the insulator. And the insulator is basically the electron doesn't move freely, but it's immobile. Or we could say it's tightly bound to the nucleus. These are the two basic kinds of materials. Now, how are we actually going to charge a conductor? Because typically, if you leave a conductor out, it becomes uncharged just in the air due to the humidity. All the large number of collisions that are taking place, any excess charge will be stripped off as air molecules constantly collide with the surface. Same thing with an insulator, it tends to become uncharged over time. That goes back to one of the original questions I asked about why the universe is charge neutral. But charge tends to neutralize because charge comes in two types. This is our charge model. There's two types of charge. Which we call plus or positive and negative. And likes repel, opposites attract when it comes to charge. Now, so far, this is just a name we're giving charge, positive and negative. Electrons carry a negative charge, protons carry a positive charge. And in order to draw a charge diagram, we want either some excess electrons or some deficiency of electrons. Now, typically, when we're looking at a normal material, not considering a plasma, it's normally the electrons which are moving. But the positive charge in the core of the nucleus is not really moving. So we could ask the question, well, how do we charge? How do you charge? How to charge? Well, one way to charge an object is by what's called the Tribo-electric effect. Now, this is a fancy name, but all this means is charge by friction. If I take two insulators and I rub them together, the insulator that has the higher electron affinity will be the one that becomes negatively charged. And the one that has a lower electron affinity, since it loses electrons, those electrons had to go somewhere, remember charge is conserved, becomes positively charged. So for example, imagine that I took a plastic rod, and I rubbed it against a piece of wool. Well, it turns out that the plastic has a higher electron affinity. What I mean by the plus here is simply friction. So you rub them against each other. The plastic has a higher electron affinity, so it steals electrons from the wool. And if I rub it, let's say I'm just rubbing kind of this end of the rod, that would acquire some extra electrons. Those electrons came from wherever you rubbed it on the wool. It's not necessarily everywhere on the wool, but just from where it was rubbed. It's important to remember that charge is always conserved. Okay, now let's say I have this plastic rod and I want to take this plastic rod and I'm going to basically bring it towards a metal can? Well, most metals are very good conductors. A conductor is an object that allows electrons to move freely, and the plastic is an insulator. So what happens when I bring the negative plastic rod, which is an insulator, towards the conductor is there's a bunch of electrons that are already close to the edge, but they're going to get pushed away by the plastic rod, and in their place are just left some positive holes, so to speak, and those extra negative electrons move over to this edge. So what I could do here is this plastic rod actually polarizes the metal can. And all this means is that it separates the charge. That's all that's meant by polarization. It means it separates the charge. This can still is electrically neutral, but because it's polarized, there's now an attractive force. So the plastic rod actually pulls the metal can towards it, simply because of this polarization or the separation of charges between the insulator and the conductor. And I can actually measure that in particular force. All right, so we've talked a little bit about the principle of charge conservation. Charge is always conserved. It can't be created or destroyed. Now this is something that I can't prove, but it's something that just turns out to be true. Charge is a property. If one object acquires charge, it must have come from somewhere. Now, this can, remember, didn't acquire any charge. Its charge was just redistributed by the presence of this insulator. All right, now what about one final point I want to make here is what's called charge quantization. Now, it turns out that the elementary unit of charge we call E. 1 E is equal to 1.609 times 10 to the minus 19 coulombs. Or C is short for coulombs, and coulombs is the SI unit for charge, or the scientific unit for charge. 1 coulomb, you can see, is a very, very large amount of charge. It's about 6.25 times 10 to the 18 electrons. So 1 electron carries a tiny amount of charge, but a coulomb is a very, very large amount of charge. So what quantization means is basically chunks. Or discrete packages. So charge comes in little packages. It's not smoothly smeared out like peanut butter, but it comes in little blotches. And the proton carries exactly a charge of plus E. So the proton carries a charge of plus E, where the electron carries a charge of negative E. And this is very interesting that these two particles carry exactly amounts of equal charge, but plus and minus.